Okay, so we're going to be looking at probability distributions. And so the basic idea is it's going to give you a graphical representation of probability and the various different outcomes of an experiment. So the goal here is going to be to create a probability distribution for various events, and then look at those probability distributions and help us understand what's going on in those binomial distributions just a little bit better. So for our first example, actually before I do that, I'll post these answers to last night's homework up on Canvas when I actually export these notes. So those will be up by tomorrow. So our first example here is just a very simple one. A probability distribution is just going to be a visual or tabular representation of the relative probability of various outcomes, which means how likely each of the outcomes are going to occur. So our first one here is just going to be rolling one die. And as far as the outcomes go, we've got 1, 2, 3, 4, 5, or 6. And the probability on each one of these is pretty simply just going to be 1 out of 6. So in each of these, we'd have 1/6, 1/6, 1/6 for all 6 of them. Now 1/6, as a fraction, is going to be about 1.6 repeating. So we'll just graph it as like 0.17, somewhere in that range. And so when we go to graph these, every single one of our outcomes, 1, 2, 3, 4, 5, 6, they're all going to have exactly the same probability, all right here at 0.17. And so this is just going to be a basic bar graph. 1 has a probability of 0.17, 2 has a probability of 0.17, same with 3, same with 4, same with 5, and same with 6. And so a lot of times you'll hear this called a uniform distribution. Every single thing has the exact same probability. For this case, it's kind of boring to look at, so we're going to just not spend too much time on this. The idea is to get a nice little graphical representation of how likely each of these events are relative to one another. So for our second example, we're going to look something a little more complicated. Now we're going to roll 2 dice. So the first question we have are, what are the total possible outcomes? So just like before, we could get a 2, a 3, a 4, a 5. We can't get a 1 anymore because we're rolling 2 dice. But we can get 6s, 7s, 8s, 9s, 10s, 11s, and up to 12s. So the first thing I want to look at is just how many different ways can you get each of these. So for a 2, there's only one way to get it. You can get a 1 and a 1. For a 3, however, you can get a 2 and a 1, or a 1 and a 2. There's 2 different ways to do that. Pause the video for just a second, take some time, think about how many ways you get each of these other outcomes. How many ways can you get a 4, a 5, a 6, a 7, 8, 9, 10, 11, and 12? So hopefully you thought about that a little bit. So we'll go ahead and just fill these in. The outcome of getting a 4, you can get 3 different ways. A 5, you can get 4 different ways. A 6, you can get 5 different ways. And a 7, you can actually get 6 different ways. Then they start going back down. 5 different ways for an 8, 4 different ways for a 9, 3 different ways for a 2, 2 ways for an 11, and again, only 1 way for a 12. You have to get both 6s. Now, sometimes it's a little bit hard to look at, and so you might see something like this to help you out with, of being able to grab a picture. And this represents all 36 different ways you can roll 2 dice, and they kind of organize them. So everything along this top row is always starting with a 1, starting with a 2, starting with a 3. These are all ending with a 1, ending with a 2, ending with all the way up to a 6. And so they kind of organize them. As you can see, if you count all these up, there's 36 of them. And if you count the ones that you want, you'd have the relative frequencies that we've got there. There's 36 altogether. So we are really more interested in probability here. So if we can get 1, there's 1 way to roll a 2, our probability very simply is just going to be 1 out of 36. For rolling a 3, 2 out of 36. For rolling a 4, 3 out of 36. And so on and so forth, all the way down. The chance of rolling a 7 is actually 6 out of 36, which is a 1/6 chance. Compare that to a 1/36th chance of rolling a 2. You're way more likely to get a 7 when you roll 2 dice. So we could fill all that in, and we could look at graphing this as a relative frequency table, or a relative frequency graph. But I'm going to actually go ahead and show you, using Excel here, rather than doing it by hand, we can save ourselves a little bit of time. So here I went through and I just put all those outcomes again, 2 through 12, and in each of these cells, I just used Excel to calculate the probability and rounded it off to 2 decimal places. So each one of these is just 1 over 36, 2 over 36, 3 over 36, all the way. And as you see, the total here is 1. There's only so many ways to roll a dice, and the probability of all of them has to add up to 1. So with Excel, the nice thing we can do is we can just highlight our data, go to Insert, and we're going to insert a bar graph, just a regular old 2D bar graph. So I'm going to do it this way. Just a regular old bar graph. And you're going to see what that probability distribution looks like. Sometimes it's nice to change the layout. Something a little bit more like that, maybe. Looks a little bit better. But ultimately, it doesn't really matter too much. And so what you can see here is that things like getting 1s and 11s are very rare when you roll 2 dice. That's why in a lot of games getting snake eyes or 2 different 1s is fairly rare. Or getting 2 6s is fairly rare. But rolling a 6, actually that's a 7. I'm not really sure why that's doing that. Anyway, in the middle here, rolling your 5s, 6s, 7s, 8s, those are pretty common. And you'll see that in the probability distribution. So those are just regular probability things that we talked about last week. Now we're going to take this and apply it to a binomial experiment. So here's our binomial experiment. A certain disease has a mortality rate of 35%. And we've got 10 people at a local hospital infected. So what we're going to want to do is find the probability that nobody dies, that 1 person dies, that 2 people die, that 3 people die, all the way up to, how probable is it that all of them die from this disease. And so we'll start off with finding the probability that 0 people die. And again, this is just a binomial distribution. And so we can just use our formula. We have 10 people. We're going to choose 0 of them first. We're going to multiply that by our success rate, 35%. 0 of them are dying. Multiply that by our failure rate. And we want all 10 of them to live. And so if we do that, we bunch that into our calculator, it can tell us pretty quickly what the probability is that none of the people die. And I don't know, a few of you yesterday found out that this is actually fairly easy to do on your calculator. It has tools for this right in it. So if you wanted to, you could certainly look for that. So this is giving me 0.01346. So about 1.3% chance that nobody dies. And we can keep doing this. We're going to find the probability that 1 person dies. And to do that, we're just going to do 10 choose 1. There's 10 different ways that could happen. Each of the 10 people could die. We have our 35% chance that 1 person dies. And then our 65% chance that the rest of the 9 people die. And again, you can use your calculator there. If you really want to know how to do this, you're looking up the binomial PDF on your calculator. It's pretty straightforward to use. And that's telling me that we've got a 0.0725. So 7.25% chance that 1 person dies from this. Now obviously going all the way through this, all 10 people, that gets really annoying. We're not going to do that. So Excel actually can do a lot of this for us. So I'm going to switch over to sheet 2 here and go for my probability. So the probability that nobody dies from our work here was 0.01346. So I'm just going to go ahead and write that in there. And our probability that 1 person died was 0.0725. So we can go ahead and write that in there. But I don't want to calculate the rest of these. So one thing I could do is I can actually use Excel to do a lot of this work for me. So I can type this formula right into Excel. If I type equals and just start typing the word combination, the very first option here is combination. And I'm just going to do 10 choose 2. Then I'm going to take that times 0.35 to the 2, because I want 2 people to live, times 0.65 to the 8, so I want 2 people to live and 8 people are going to die. And Excel is going to tell me, hey, that's 0.17565. Excel can do all that math right in there. The other thing Excel has is if I start typing binomial, it has a calculator for binomial distribution. And it's going to ask me for, first of all, the number. So I'm going to say for this one, I want 3 people, 3 successes. The number of trials, you see how it's highlighting there. We're doing 10 trials. The probability, so that was 0.35. And this last one is whether we want it to be cumulative or not. So we're just going to type in false. We don't want to do cumulative, we just want to do this one. And hit enter, and I've got my probability that 3 people die. And we just keep doing that. Binomial distribution, oops. I double click on it. This time we want 4 out of 10, 0.35, and false. And it'll calculate that, 0.23. Best part about Excel is I don't even need to keep typing these. I can just highlight the box, drag it all the way down, and it's not going to work for me, is it? We'll just keep typing those in then. So binomial distribution, this time we want 5, 10, 0.35, false. This time we want 6 out of 10, 0.35, and false. Seven out of 10, 0.35, and false. And I'll just go ahead and fill these in real quick. And again, your calculator can do this too. There's a feature right in there that'll tell you, that'll just let you type in these 3 numbers to tell it that we want 9 people out of 10, and there's a 0.35% success rate. Your calculator won't need you to do false, but go ahead and look that up if you feel like it. You can always use the formula, it'll always be there, but this one, kind of a nice simple way to make your life a little bit easier. So, that one you see there's scientific notation, there's an absolutely minuscule chance that all 10 people will die here. Last thing I want to do is I'm going to go ahead and sum these up. So if I add up all these things, think to yourself real quick before I do this, what should this add up to when I hit enter? And you'll see there, within a rounding error, we've got basically 1. The probability of any given number of people dying should add up to 1. Probability totals are always 1. So the last thing we're going to do here is just go ahead and graph this. So we'll insert our chart right there. And you'll see we've got probability graphed. So there's a small chance that nobody dies, and our peak chance here is that 3 people die. Again, if we have 35% chance that they die, it would make sense that out of 10, somewhere in the neighborhood of 3 or 4 is what we would expect. Those are the most likely. That doesn't mean it can't happen that nobody dies, or that it can't happen that 8 or 9 or 10 die. And there are numbers here that are just really, really small, too small to see. And so that kind of gives us a better picture of what's going on. More people are going to be over here, and there are going to be a few times where something like this happens. And it's fairly rare, but it still could happen. So today for homework, all you're going to be doing is taking a look at graphing these different probability distributions. These first few are just regular probability. They have nothing to do with that binomial distribution that we've been talking about. You're just looking at, jar contains 5 balls. You draw a ball at random. What's the chance that you get 1, 2, 3, 4, 5? Same kind of thing here. Just a different chance for each one. I didn't put 17 in there, but you have to do 17 as well. That's a binomial one. Number 29. These are just back to straight binomial probability. You don't need to graph anything. Just go ahead and compute all of those probabilities. And same thing with 33, just binomial probability. A little bit more work from yesterday. Again, take a quick look up here in the note.